This is lesson 2.7 and it's about fitting a model to data. So this time we're going to have data in a model form or in a graph form, but we need to figure out which model it is, whether it's y equals k times x squared, or y equals k over x, or y equals k over x squared, or y equals k times x. So let's review a little bit. You can see the different graphs over here and what the relationships are, what they look like. Make sure you can identify the graph and identify the variation equation that goes with the graph. So we know y equals kx squared looks like a curve going up in this first quadrant, where the second graph, y equals k over x or y equals k over x squared, is a curve going down in that first quadrant. Or that third graph, y equals k times x, is a straight line going up in that first quadrant. Okay, so let's do an example and let's take some data and figure out what variation equation applies to the data. So example 1a, we have time t in seconds, and it starts at 1 second and it goes all the way up to 3 seconds. Then we have distance fallen in d meters, and it starts at 4.9 seconds and it goes up to 44.1 seconds. The first clue that I would look at is, I see as time is increasing, the time values are getting bigger, the distance is also getting bigger. So they are both getting bigger. So that would tell me right away that it's a direct variation. And I can eliminate my indirect or my inverse variation equation. So I only now have choices of y equals k times x squared or y equals k times x. The next step I would do is I would graph this. And you should have already watched the video on how to graph these in your CAS and know how to do this. So I would graph it, and looking at that graph on that scatter plot, I see that it actually looks like a y equals k times x squared because it matches similar to this graph. Now I'm going to check that and see if that's right, and I'm going to plug in t is 1 and d is 4.9 to see if that works in my y equals k times x squared formula. So if t is 1, and I will rewrite this with d's and t's instead of y's and x's. So I'm going to say d equals k times t squared. So then if t is 1 and d is 4.9, 4.9 should equal k times 1 squared. In this case, k should be 4.9. Okay, let's test that with another set of data. So let's do 1.5 and 11. And I'm going to work up here so I have more room. So I have my d equals 4.9 t squared because I solved for k. So I'm going to plug in 1.5 for t. So d equals 4.9 times 1.5 squared, and that should equal about 11. So I multiplied 1.5 squared times 4.9 and I got 11.025. That is very, very close to that 11 for the d. So I know that this is a y equals k times x squared variation equation, and I'll write it in the d equals k times t squared format. Okay, so the next part of that down here, use your equation to predict how far an object would fall after 6.5 seconds. So the distance it would fall equals k, we said was 4.9 times 6.5 seconds, and I got to square that, and I should get, when I work through that math, 207.025 meters. That's how far it'll fall in 6.5 seconds. Okay, part B, or example 1b. Now we have new data right here, x and y. And they want us to find a variation equation for that data. Well, the first thing I'm going to look at is x is getting bigger. It's going from 1 up to 3. and y is also getting bigger. So I know it's probably going to be one of the direct variation equations. So it's either going to be y equals k times x squared or y equals k times x. The next step I would do is graph it. So make sure you do that in your calculator. And you will notice when you do that, it looks like a y equals k times x squared graph. It looks like this one right there. Make sure you can graph that in your calculator. So now I'm going to test that using some of the points. I'm going to use x is 1 and y is 3.2. So 3.2 equals 1x squared. Oh, I apologize, that shouldn't be 1x squared. That should be k times x squared, and x squared is 1. Let me erase that. It doesn't want to erase, so I'll rewrite it down here. 3.2 equals k times 1 squared. I just used those first coordinates right there and plugged them in. And I have 3.2 equals k. Oh, okay, I'm going to continue on. I said k equals 3.2. I'm going to plug back into my direct variation equation, and I'm going to say y equals 3.2x squared. So now I'm going to test it with another one of my coordinates to see if it works, and I'll do 2 and 12.8. So I'm going to say y equals 3.2 times, I'm going to say the x value, I'm picking 2 squared. Y equals 3.2 times 4. If you multiply that, y equals 12.8, and that matches what it says up here for that y coordinate. So then it is correct, and my general variation equation is y equals 3.2 x squared. So my direct variation equation for that data. So those previous examples were both direct variation examples. Now let's talk about a model for inverse variation. So here's the data from Jenna's experiment at the playground. So if you look in the book on page 115, it talks about her experiment on the playground, and it has to do with the seesaw. We talked about that law of lever. So what she's doing is she's testing whether the distance has to change based on the weight of the person in order to balance the seesaw. So remember we talked about if you weigh less, you can be further away from that pivot point on the seesaw. If you weigh more, you need to be closer. Your distance needs to be less. So it's an inverse variation relationship. So if we have this data here, and we see as weight increases, weight's going up from 70 to 206, our distance is decreasing. It's going from 1.7 yards down to 0.6 yards. So we can see it's definitely an inverse variation relationship. Now, how do we know? Because if we have our graph of our data, how do we know whether it is going to be y equals k over x or y equals k over x squared? How can you tell the graphs apart? Well, the first thing I would do is I would test it. So let's rewrite it as d equals k over w or d equals k over w squared. And we got to test and see which one it is. So I would use the points and test it with these points on the table. So let's try d equals k over w first. Let's solve for k, just like we're following our steps. So we're going to pick 2 points. We'll use the first two, just for easiness, 70 and 1.7. So d is 1.7. Make sure you put them in the right spot. And w is 70. Let's solve for k. We multiply 1.7 by 70. Okay, k equals 119. So in step 3, I'm going to rewrite it. D equals 119 over w. Step 4, I'm just going to pick 2 more points, but I'm only going to use the w value to see if I get the correct d based on it. So I'm going to say D equals 119 over 109. And I should get 1.1 as my answer for D. So 119 divided by 109 is, when you divide them, you get D equals 1.09, which is pretty close to the 1.1. So now we can test it with the D equals K divided by W squared inverse variation equation and see if that one works better for this data. Okay, now we're going to try it for D equals K over W squared. So that's step one, we wrote our equation. Step two, let's test it using two coordinates. We'll pick the first two just because it's easy and they're there. It doesn't matter, you can pick any of them. So we're going to say 1.7 equals K over 70 squared. We solve for K, make sure you square the 70 first, so you'd have 1.7 equals K over, okay, I squared the 70 and I got 4,900, so then I multiply 4,900 by 1.7 and I get K is 8330. Step 3, I plug it back in, I say D equals 8330 W squared, and step 4, I'm going to use another set of points. This time we'll use 140, let's use 170.7 just for something different. But I'm only going to use the 170. So I'm going to say D equals 8330 divided by 170 squared. And I should get, for my D, an answer of 0.7. So let me work through the math. Okay, when I work through the math, I get D equals 0.288. This is not close to that 0.7, so it looks like this graph here is actually going to be a D equals K over W graph, not a D equals K over W squared.